Okay, so today and tomorrow our lessons are graphing trig functions, part one and part two. And this is kind of the flip side of what we've been covering before our break. Before our break, I had done a lot of work on a unit circle. And I'm going to flip to the next slide just to kind of, well, this is your next slide. Okay, we would have spent a lot of time talking about like what happens in like a circle along these lines here. And that is one tool we have in our arsenal to solve questions. But another tool we have is to know what the graph of sine and cosine and stuff look like as well, because that's also a useful skill to have as well. And a couple of you have already probably seen this before. A sine graph, don't want to give this away, but we've done this in physics, is basically a wave. It just goes up and down and up and down. What I want to do today is talk about why it is that wave curve, and then how this is another way that we can use to solve problems, so that you actually have an algebraic sort of way, but you also have like a graphing calculator sort of way as well. And sometimes one way is better than the other, but often many of these questions I'll give you, you can solve using either method, depending on, I don't know, which one you like better. So let's start by graphing this thing though. So let's go back to this slide here. I want to make a table of values. So I'd like to do this in degrees just to start with first. And then after we finish doing degrees, then I'll convert to radians. So on one axis, I'm going to put x. On the other axis, I'm going to put y. And then I'd like to, it's going to be a fairly long table of values, by the way. So let's start with x being 0 degrees. So you guys have your calculators nearby. Put your calculators into degrees. Make sure we're all in degrees so we're on the same page. And then type in sine 0. Just go with that. Sine 0 is 0. Okay. In order to make this kind of nice increments, rather than going by like 1 degree and 2 degrees, that's kind of ridiculous. I'd like to go in larger increments. So a good increment would be to go up by 30. So let's do sine of 30 now. What happens when you get to sine of 30? 0.5, perfect. Same thing. Okay, let's go 60. 0.86 repeating? Well, not point, just 0.866 though, yeah. Okay. Then let's do 90. $120. Yeah, it actually goes back to 0.866. I'm going to talk about why it does that in a little bit, but just go with it for now. It's going to be a super long table of values, by the way. When do you think I'm going to stop this table of values? What would be a logical number to end it at? 360 is correct. Why? It's all the way around a circle. Yeah. Okay, so I'm just going to fill out some of these. 150, 180, 210. Can you guys just kind of fill this out on your own here? 270, 300, 330, and 360. Can you guys basically find all of those values in 30-degree increments, all the way up to all the way around once around a circle? Find all these values. You're going to discover it's actually the same four numbers over and over again in some orientations of positives and negatives. And then we'll plot it on a graph and we'll talk about why this occurred that way. I'll let you do it first. I actually have them memorized, so I'll just write them in a second. You need a should get you a new one just for the diploma, just in case. I'll lend you one of mine. Yeah, I'll just lend you one of mine then. On yours, one thing you could do is just press Enter one more time and move it up. Yeah. Seems kind of silly to have to do that, but I guess it would work. Okay, have you guys noticed there's a bit of a pattern to this yet? I don't know how far you've gotten. Well, until a certain point. Fair enough. I wanted to give you guys a chance to explore it yourself first. So it actually, now, I mean, it's not just these numbers. We did these things in increments of 30, but I feel like this is a good way for us to be able to graph this. Let me go back to the graph now. I'm going to try to break these things up into 30-degree increments. So I'm going to make every 2 be 30 degrees. So this will be 30, 60, 90. I'll just write in 90 right there. 120, 150, 180, 210, 240, 270, 300, 330, 360. I'm only going to write them in just like larger increments there, otherwise it gets way too busy. Okay. Now watch what happens when I plot this. And why don't I make this be 0? I'll make that be 0.5. I'll make that be 1. Make that be negative 0.5 and negative 1. So for Jessica and Michael, this is your basic like oscillating wave kind of curve that we've been learning about in physics as well, right? So watch what happens when I plot it. 0 goes with 0. 30 goes with 0.5. 60 goes with 0.866, which is about right about there, give or take. 90 gives you 1. Then it starts coming back down again. And back down again. And then at 180, it's back down to where it starts. It's basically what we've seen here is the rise of like the peak along those lines. And then it starts going into the negatives. It does the exact same pattern, but it goes into the negatives. Then it goes down to negative 0.5 to negative 0.86 to negative 1, and then back again, back to negative 0.86 to negative 5, back to 0. And this is known as the sine graph. Basically this wave pattern. I'll give you a second to kind of catch up with your plotting of points here, because I'm sure I went a little faster than you guys did. Where'd that McDavid jersey go?
What's that?
Where'd the McDavid jersey go?
I took it off a bunch. I didn't want to get it dirty.
Neither does he. Well, that was good. Okay, now this graph right here actually doesn't just stop at 360 though. You're still plotting. Give me a second still. This graph doesn't just randomly stop at 360. What ends up happening is the graph kind of continues and it goes back up and down, and it basically repeats this pattern over and over and over again, right? Because what's happening, if I can now use the next slide to kind of reference things. Okay, where's my next slide here? Let me just delete these ones actually. I'm getting in my way now. There we go. Okay, let's talk about why this graph works like this. Okay. Thanks, Jessica. If we were to have 0 degrees, see how 0 degrees would basically be like you wouldn't even have a triangle in here. So I'm trying to make a triangle in here. If you can envision that. If I had 0 degrees, it basically would just be flat across. Now, what's the formula for sine? Well, sine is opposite over hypotenuse. Well, the opposite would be how tall you make this triangle versus the hypotenuse. And in a unit circle, we just always make the hypotenuse be the value of 1. That's why we call it a unit circle. So if your hypotenuse is always 1, then it's really however high your opposite is divided by 1. Now at 0 degrees, you don't even have a triangle really, right? So how high is the opposite? Well, 0, right? It's like you go over, you go up nothing, then you come back again. So does that kind of explain why sine of 0 is 0? But like what happens when you have 30 degrees right here? Well, sine of 30 degrees means it's your opposite over your hypotenuse. Well, your opposite is about half the circle, right? From here to here. Do you see how that's got a y value of about a half? Well, then what happens when you get to 60 degrees? Do you see how your opposite side now is getting even taller? What happens when you get to 90 degrees? 90 degrees, you go all the way up. You actually don't even go over whatsoever, and you come back down again. Well, your opposite, if you can even call it an opposite, is 1. Your hypotenuse is also 1. What's 1 divided by 1? 1. That explains why sine of 90 is 1. Well, then now look at these quadrants here. Do you now see how the opposite side right here is starting to come back down again? And so what's really happening is the opposite is getting bigger and bigger and bigger and bigger and bigger. And then once it reaches the top, the opposite side starts getting smaller and smaller and smaller and smaller. And this really corresponds to the graph going up and then back down again. Well, then the opposite side of your triangle, down in this quadrant right here, starts to become an opposite that is a negative opposite, which now starts to explain why your opposite starts going in the negative direction until it rotates to the point where it gets all the way down to here, at which point here, basically the opposite side is as big as negative 1. And then as it keeps rotating further and further and further, the opposite side of your triangle gets smaller and smaller and smaller again. I'm running out of room over here, until it eventually gets back to 0. And so I hopefully have some slides on here that have some pictures showing the same sort of concept. But as you go around the wheel, really sine is opposite over hypotenuse. But in a unit circle, we're going to call the hypotenuse 1. That's why we call it a unit circle. Okay? So if the hypotenuse is 1, all we care about is your opposite. Here it's getting bigger and bigger and bigger, and then smaller and smaller and smaller, and then negative bigger, negative bigger, negative bigger, and then negative smaller and smaller and smaller until it gets back to 0. Except, do you have to go around the circle just once? Well, no, you can keep going around the circle over and over and over again, explaining why the sine wave basically goes up and down and up and down infinitely. So that's what the sine graph looks like. So here's some more pictures kind of trying to illustrate the same concept here. But the long and short of it is that your sine value is really your y value. It's that opposite or y, however tall this point happens to be. So it goes up, it comes back down again. It goes negative, comes back up again. Goes up, comes back down. Goes negative, comes back up. Rinse, lather, repeat, do it over and over again, hence the sine curve. Does that make sense? Okay, let's try cosine. Repeat the exact same task I asked you guys to do to start the class. I know it's a little tedious, but I want to go through the motions of it. And do that with cosine now. So do like x and y, and do again 0, 30, 60, 90. And again, try this yourself. I just want you to experiment and play with it so that you can kind of come to the conclusion without me telling you. Make a really big table of values and then try it again. It would. So let's just do it in degrees for right now. Because, I mean, if you're in radians, then rather than using 30 and 60, you'd have to use pi over 6 and pi over 3. I think just to start with, it's easier to do degrees. These spinners really are distracting. What are you noticing so far? It's the same silly numbers over and over again, but a different order, hey? And it has the same sort of pattern to it. Let me know if you don't have what I put on the board there. It's the same numbers. It's actually, truthfully, it's actually in the same order that it was before. So let's try graphing this one now. I want to compare the two. So I'll do the same thing. I'll make this be 1.5, make that be negative 0.5 and negative 1 on the y-axis. And then, what did I do every time? Every 2? 1, 2, 3, so that'll be 30, 60, 90. 1, 2, 3, that'll be 180. 1, 2, 3, 270. 1, 2, 3, 360. And I'll plot the exact same thing. You should get, it actually has the same sort of pattern to it. It actually looks almost like a parabola when you're done. You guys able to get this graph? Let's talk about why this exists. First off, this is actually not the whole graph. If we were to allow this pattern to continue, what you'd actually discover is that it basically goes down and back up again over here. And if you were allowed in the negatives, it does the exact same thing. Cosine actually has the exact same wavy pattern. That's my last class YouTube video done. Cosine has the exact same wavy pattern that sine does, only it's slightly offset, but it still goes up and down. Now, in the previous slide, I talked about how really your sine of theta value is really your y value. Remember how it was opposite over hypotenuse? But we said it's a unit circle, so therefore the hypotenuse is 1, so it's your opposite divided by 1, which may as well just be your opposite, and your opposite value is essentially whatever your y value is. Let's use that same logic for cosine. What is cosine equivalent to? Well, cosine would be equal to your adjacent over your hypotenuse. But again, your adjacent value would be, sorry, your hypotenuse would be 1, so let's just skip that. In this triangle right here, your adjacent value is really your x value. So let's talk about what's happening to your x value as you go around the circle. So let me just find a circle to go with here. Let's use this one here. If you were to have 0 degrees, you go all the way out, don't even go up and come all the way back. How much x value do you have? 1. Well, as the circle gets bigger, what happens to your x value right here? See how the x value is getting smaller? And then up to here, see how the x value got even smaller again? Until you go straight up and down. Well, when you go straight up and down, what sort of x value do you have? You didn't have any. You didn't go side to side. You literally went up and then back down again, right? So that's why cosine of 90 is actually 0. Well, then you start going into the next quadrant. What happens to your x value? Becomes negative. And as you keep going, your x value gets bigger and bigger and bigger until eventually at 180 degrees it becomes negative 1. Makes sense? Because it goes all the way out 1, doesn't even go up or down, and comes back again. Well, now compare that to your graph right here, the one we drew. See how your x value starts at 1 and is slowly but surely getting smaller? As you go around your circle, that's here to there to there. See how the x value for all those triangles is slowly but surely getting smaller until you get to 90. At 90, there's not even a triangle. Then your x value starts becoming negative. Bigger x negative value. Bigger x negative value. Until eventually you get to the spot right here where it goes all the way out and back, negative 1. Which is why this down here is negative 1. Then in the next quadrant, your x value starts to come back towards 0 again. Your x values keep getting smaller and smaller towards the 0 value, but they're still negative. And then here, your x values start becoming positive again. See how they keep getting bigger, positive? Essentially, cosine and sine are almost the exact same graph as each other. And one of the things I'd like to do, I found this actually helps kids, is make a manipulative to draw for sine and cosine. So this is like back to grade like 4, arts and crafts. See if you can follow this. First thing I need you to do is fold the, there's no hamburger and hot dog folds? Yeah. Okay, do a hot dog fold right down the middle. So that you have one guy like this. Okay, and then, I don't know, fold it the opposite way, whatever that would make it then. Hamburger fold, I guess. Like that. And then do one more of those. So what you're looking to do is make this into like an 8th of the size of paper. So you have one of these when you're done. Yeah, like the one you just did there, yeah. So ideally you have one of these. And then unfold it. What you should have now is a sheet of paper that has like 8 little boxes to it. And then you're going to want some sort of nice colorful drawing device. That's right, drawing device. So maybe just share these. Do this however you want. So here's what I would recommend you do. On this axis right here, right around the middle, this is going to be your angle. So see how I'm drawing this as like your angle along this axis right here? And then this, you have to draw it just right up against the edge here. Along this side right here, this is your y value. And what we're making is a graph that looks like this. This is your y value right here compared to your angle along the edge. Okay. And then each of these little quadrants is going to be 90 degrees. So the first one's going to be 90. The middle is going to be 180. The next one's 270. The edge will be 360. And you're starting at 0. So it should look something like this when you get there. How tall is the top up here in terms of y value? Yes. Yeah. So the very, very top here is 1. And the very, very bottom would be -1. That's usually implied, but if you want to write it on there, you could. One more thing I want to do here. In each one of these like kind of sections here, I'm putting which quadrant it is, because what we're really doing is we're talking about what happens as the circle starts going around. So you guys remember like the quadrants 1, 2, 3, 4, right? That's really what's happening here. So this is talking about quadrants 1 through 4 there. So that's kind of our basic setup. My high school math teacher made one of these with us, and it stuck with me even to this day. So I found this very useful as a visual. Okay. Take a pen and flip it for the next person's here. So trade me for a new color here. Doesn't really matter. We're gonna need 3 colors when we're done. Okay. So what I want to do in one color now is draw what a sine graph looks like. So here's what sine's gonna look like. It's gonna go all the way up to the top, all the way back down to the middle, all the way down to the bottom, and back up again. And this is what sine of theta would look like. See that? Sine starts at the bottom, and it waves up to the top, down, and up again. That's what a sine graph looks like, which is the first thing we graphed today. Now, a couple of you guys drew, now don't change yours because they're not wrong, but a couple of you drew yours like very like square. Yeah, you see how like the second one there had more of like a curvy shape to it? It's not the end of the world, but you do want to draw it as kind of like a wave sort of pattern to it. So that's what sine would look like. And then flip pens to another one after this, because we're going to draw cosine afterwards as well. The way cosine worked is cosine starts at the top, goes down through 90, bottom through 180, back up through 270, and like this. So the pink one is now what cosine would look like. More or less like a U, maybe a V. I mean, it's kind of like it has to have a little bit of bendy waviness to it still. And then we just write this one in here. This would be what cosine of theta looks like. My high school math teacher had us make these, and I felt they were very useful because the cool thing was is now I had like a little manipulative that I could just kind of fold up and keep with me when I needed it because it helped me visualize things. I want to go back. Earlier today, I had you guys answer an old diploma question where it basically wanted you to know where cosine of theta equaled 1/2. You guys remember that from somewhere earlier today, cosine of theta equal to 1/2? Here's how I solved it from last week, I would have done this. I would have drawn a little bit of a circle like this. I would have used the cast rule and went CAST. Then I would have said, well, where is cosine positive? And I said, well, cosine would have been positive in this quadrant here or in this quadrant here. And then that let me know that there was going to be two answers. Now consider our drawing instead. Where is 1/2 on this diagram here? Where would the line of cosine of theta equaling a half be? There. Where is the pink graph? Now, I don't want to color on this one again, but imagine that I put a line straight across up over here at 1/2. Where does the pink graph cross with this line? Which quadrants? Quadrant 1 and quadrant 4. Where was cosine positive? Quadrant 1 and quadrant 4. See how that works there? And what we could do once we get better at using our calculators is we could solve it using this. Or we can use our graphing calculators and intersect where these points right here would be. But it kind of shows you how that would work. Not only that, this helps you visualize the symmetry, because however much angle it takes to go from here to here to get to that intersection point right here, wouldn't it be the exact same amount of angle going backwards? Which kind of explains why that angle can just be subtracted from 360 to find the other angle we're looking for. And we can do this in a lot of different ways. If I were to then ask you where, say, the sine of theta equals -√3/2. Well, I don't even need to care about what √3/2 happens to be, but where would sine of theta equal a negative number? Well, here's a negative number. Where is the sine of theta, the yellow graph on mine, going to equal that negative number? In quadrants 3, 4. Now let me go back to what we did last kind of day there. According to my cast rule, CAST, where is sine going to be negative? In this quadrant here and in this quadrant here. See how there's kind of an angle in between there? Well, that same reference angle, if you can kind of envision the symmetry, wherever this happens to be, right about here, let's say it's right about there, right? You're looking at the yellow graph. From here to here is your reference angle. But from here to here is also your reference angle. See how it's kind of symmetrical on both sides, that distance right there? Well, it's kind of the same thing right there. That reference angle is the same thing from this one to that one. So I want to use this diagram as we kind of solve some of the following questions, because I think it kind of helps you visualize it. One last thought. How are sine and cosine related to each other? I have a silly little thing I use to help kids remember it. A cosine graph is a sine graph that failed to grade. Look at them. A cosine graph is a sine graph that failed to grade. Do you see how literally every point on the cosine graph is like 90 degrees behind the sine graph? This point right here, well, cosine graph's just back there. This point down here, that one's back there. This one over here, this one's just behind it. So literally, like a cosine graph is like sine graph's little brother. They're identical in all ways, except one of them is always just shifted behind the other one. This helps explain why there's two answers when you plot it on the circle, but more than that, if we were to actually consider the graph now to be allowed to go up and down, this explains why there's actually an infinite number of answers, because here's the first two answers, but then you can go around the circle and find two more. You can go around the circle and find two more, and go around the circle and find two more. That's that whole general solution concept of how you just keep going around the circle 18 million times. So I like to think of this as like two sides of the same coin. This is one way of solving things, and like that unit circle is another way of solving, but they really kind of mesh, they meet together. Okay, let me do some more of my examples here. This was just to talk about how cosine is adjacent over hypotenuse. So just a reminder then, the adjacent would be your x value. Your hypotenuse, though, is 1, so therefore your cosine is whatever your x value is. And your x value is going to get smaller and smaller, then become negative and negative, then come back again. That's a whole pendulum kind of concept going back and forth. Okay, I need to talk about some properties of these graphs. And so we can use just the one we made in front of us to talk about properties here. So, okay, you guys learned about amplitude before in physics. Do you remember what it is? What's an amplitude mean? how tall a graph is, how tall the wave is. So how tall are these waves here, either one of them? How high do they get up to? Yeah, 1. So that's the same thing for both. For cosine or for sine, they both have an amplitude of 1. That's as tall as they get. They get as high as 1 and as low as negative 1. Because they're based on a unit circle. Now we can change that, by the way. We'll get to that in a bit. But for now, there is only 1. What's a period? How long it takes for it to do a full rotation. How long does it take for this graph to go all the way back around again? Or in radians? 2 pi, yeah. So it's either 360 degrees or 2 pi, depending on whether you're talking radians or degrees. But your domain is the x values. Now x in this example though, x is really being replaced by theta. So what sort of angles are allowed? Let me put this a different way. Are there any angles that are not allowed? Could you take the sine of 5? Sure. 1,000? 2,000,007? It's anything. So in this graph right here, your domain is element of the reals. Only rather than writing as x is an element of the reals, you might see it written as theta is an element of the reals. Just because really theta is x, like the angle is your x value. So there are no non-permissible, there you go. There's no non-permissible values for x or theta, but there is for the range. I want to take a stab at what the range would be on this graph. That's fantastic, yeah. Only we'd have to write it the other way around. It goes from -1 to +1. Or another way of writing it would be y is between +1 and -1. It can't get bigger than 1. It can't get smaller than -1. Which kind of makes sense because it's based on a unit circle. Okay, harder one now. X-intercepts. We should make sure which one is which because it now makes a difference. So why don't we go with this one being cosine of theta and this one being sine of theta, because up till now it actually didn't make a difference, but it does for the next few things here. Where are my x-intercepts on the cosine graph? That'll work. Let's also write them in radians. Anybody know what 90 was in radians? Pi over 2. You'll get better at it the more you do it. Don't stress that you didn't know that off the top of your head. Like you will learn it, I promise. Just the more familiarity you have with it, the better you get. 270 is 3 pi over 2. Remember, each time you go around a quadrant, it's half of pi. Okay, well, where are your x-intercepts on the sine graph?
0.
That'll work. 0, 180, and 360. Or putting those into radians. 0 is still 0. What was 180 at? Pi, yeah. And 360 is 2 pi. Essentially, the cosine intercepts are on the half pi increments, and the sine intercepts are on the pi intercepts. Another way of thinking about it is like, you ever see those grandfather clocks that like chime on the hour or on the half hour? Think of it this way. These guys chime every half hour, and these guys here chime every hour. That's all. They're out of sync by half an hour on each, right? But this is actually not it. I should say like etc. after these ones here. Because even though I didn't draw it in my diagram, does it not make sense that this graph is going to keep waving up and down till infinity? And so, I mean, if I asked you for another intercept on cosine, 57 over 2 pi would work. 97 over 2 pi would work. You know what I'm saying there? Whereas over here, so long as it's an even number, so long as it's not an over 2 pi, it would work. So 18 pi would work, 19 pi would work, but not 19 over 2 pi. 19 over 2 pi would be over here. Does that work? Okay. Y-intercept of the sine graph. All right, let's do cosine first. Y-intercept of the cosine graph? 1. And the y-intercept of the other graph? 0. You'll just need to memorize those or just kind of know where they are. Okay. The last one, they don't have asymptotes. Sine and cosine don't. Tomorrow, when I talk about tan, cosecant, secant, and whichever one I missed, the remaining 4 identities, those ones all have asymptotes because those involve dividing things by each other. But for right now, we don't actually have any asymptotes. How am I doing so far? Does that make sense? Yes, it should. Thank you. Good catch. I put those in the backwards order, didn't I? 0, 1. Okay, so far so good? Okay, well, the next thing I need you to know is that just like with every other graph, you know how we can do things like squish them, pull them out, move them up side to side, flip them upside down. Yay, that still exists. Here's the good news though. The more we've been doing this, like the more it's gonna sink in. So like it probably won't be as bad as the first time we did it back in February, because like you'll know these rules slowly but surely over time. So let's talk about some transformations here. You guys don't have color on yours, so why don't you imagine that this blue graph right here is just your regular sine graph? And the reason why I know it's the regular sine graph is you see how that it rotates all the way up, all the way down and back again, and it lands right there, well, not halfway, but most of the way between 6 and 7. See where it's landing? It's landing at 6.28. The period of a normal graph, the blue graph, would be finishing at 2 pi. So this guy right here is the sine of theta graph. Anyone want to take a stab at what the graph is that's this red graph on here? What would make it shorten up like that? What would cause it to do that? What causes the graph to squish in? What do you have to do to make it squish in like that? Yep, so it ends up being sine of 2 theta. If you make it sine of 2 theta, it actually squishes it in. And so this red graph on mine here, here's another way of approaching it. You see how there's now 2 curves in the spot where there used to be 1? Like just consider it up to this point right here. See how the blue graph went up and down just once? That's your regular sine theta graph. Do sine of 2 theta, and now there's 2 of them shoved in there. How would you lengthen the graph and make it the green graph? Yeah, you'd make it sine of 1/2 of theta. That would actually pull the graph outwards, making it take twice as long as it normally would. I think this is the best way for you now to be able to interpret how the 2 and the 1/2 work, because like if this line that I drew right here is where normally the period of a graph would be, hopefully you can see this red graph, there's now 2 of them shoved in there. Well, that makes sense. Now there's a 2 in the formula. Right? If there's a 1/2 in front of there, this green graph, I actually only got half of the curve in there. The other half is afterwards, right? So now you can actually visually see how that 1/2 and that 2 do the opposite of what you think they do. The 2 squishes it in, the 1/2 pulls it out. Okay, so let's talk a bit about some of these definition terms that I kind of used on the previous slide. The amplitude then is how far the graph goes up or down. Okay. Basically what you want to do is if you want to change the amplitude, we want to stretch it this way. How do you make a graph go this way? What do you do to a graph to make it taller? Where does the value go? Before, yeah. So again, let's use this graph as our baseline here. Let's make the red graph. On this one here, the red graph is the standard graph. So I'll just make red be sine of theta. See how the red graph gets as high as 1? See how the green graph got as high as 2? To make it taller, make it 2 sine theta. The 2 just makes it taller, right? Whereas the blue graph would be 1/2 sine of theta. Because it's actually not taller, it's actually shorter instead. You guys kind of visualize how that works? Cool thing about this one here, did the intercepts change? No, look, your y-intercepts or your x-intercepts are all in the exact same spot. All that's happening is the graph is becoming either taller or shorter in terms of what we call its amplitude. So for what I have written here, the amplitude is the number that goes like right in front of sine or cosine. If you do a 2 or a 3 or a 1/2, it's what affects its amplitude. In physics, amplitude would be like how loud it is, if it's like a sound wave. Makes sense. Okay, period then is how far it is stretched side by side. Now, the normal period of a graph would be 360, or 2 pi. But if you stretch it out or in, that could affect things. So the basic concept is you want to take 2 pi or 360 and divide by whatever your b value is. So let's say that you don't have any number in front of it there, and it's just 1. Well, then 2 pi divided by 1 is 2 pi. Your period's 2 pi. For us, that would be this red graph. See how the red graph finishes at 6.28 right here? Whereas the green graph, see how the green graph has been shoved in? Well, if the value right here to shove it in would be at 2, you know how a 2 would squish it inwards? Well, then watch this. 360 divided by 2 would give you a period of 180. Well, look at this. Now this is only, well, let me not do it in degrees. Let me do it in radians. 2 pi divided by 2. 2 pi divided by 2 would give you pi. You see how on the green graph it repeats itself by pi? See how the green graph finally repeats itself as of pi? Long story short, maybe I'm getting too confusing here. If you want to try to calculate what the period of something happens to be, all you have to do is divide by that coefficient value. So if the coefficient value is 2, cut your period in half. If your coefficient was 3, divide it by 3. If your coefficient was a half, make it twice as big. So let's just talk through these ones here. You don't even need to write them down. Let's just talk through them. What would the amplitude of this sine graph here be? What's the amplitude of any sine graph? How tall does it get? Yeah. And you know what? I can tell you that because there's a 1 written right there. We don't usually write the 1, but that makes sense. So what happens when I put the 5 in front of it? Amplitude is 5 times bigger. All we've done now is rather than this graph going from -1 to 1, it's now actually going from -5 to 5. It's just taller. If you make it 1/2 sine theta, 1/2. What would the -3 do? Yeah. So all that happens is rather than this graph going up and then down again, it's actually going to go down and then up. It's just going to be like, can you guys picture how that's going to be flipped? So rather than starting this way, I mean, think of like, you know how we're supposed to go around the quadrants this way? Well, all that's happening is now you're going around the quadrants the other direction. That's all.
You still go -3 to 3.
Yeah. Except in terms of amplitude, by the way, I should point out the amplitude is still considered to be a positive number. We never make the amplitude a negative number. We just always care about how tall the graph is. Because we kind of recognize that it's always going above and below ground. So yeah, the amplitude is 1, the amplitude is 5, the amplitude is 1/2, the amplitude is 3. We just recognize that this graph is actually going down before it goes up. That's all. Okay, so let's talk about the period here. Let's do them in both radians and degrees to practice. So what's the period in degrees of your normal sine graph? In degrees, it's usually 360 to get around a circle, right? Or in radians? Sweet, 2 pi. What if I put a 2 in front? What is this doing to the graph? It takes the graph and it does squishes it. So rather than being 360, it's now half as much. Now the graph repeats itself every 180. Or if you want that in radians, it happens every pi. Essentially, this 2 right here, just divide 360 by 2. But what happens if you're dividing by a third? You're actually timesing by 3. So 360 times by 3 is a 1080. Right? What you're doing is you're actually pulling the graph out. This would be like taking a slinky and like pulling it way out, like you're stretching it past its capacity. Right? What is 1080 going to be in terms of pi's? How'd you figure that out so fast? Yeah, it's 3 times bigger. So if it used to be 2 pi, 3 times bigger is now 6 pi. A lot of kids, they get thrown off by pi, but ignore pi and just deal with the number in front of it. 2 times 3 gives you 6. 2 of apples times 3 gives you 6 of apples. 2 of pi times 3 gives you 6 of pi. What's this negative going to do right here to the graph? A bit like this. You know what that ends up doing, actually? Sometimes it does nothing, or sometimes it ends up making it look like it's upside down anyways. If the graph was supposed to go up and then down like this, if that's what it was supposed to do, and you flip it side to side, what ends up actually happening is it's the same thing as flipping it upside down. This point would come over to here. This point would come over to here. You see how like I'm flipping it that way there? It ends up looking like it flips upside down, but the more important point is the 4. The 4 is the important thing. It would take your graph and also squish. I mean, not only do you flip it, but you also squish it in 4 times. So if it was 360, 360 divided by 4 is 90, which is half of pi. And the more you do the whole 90 to pi sort of conversions, the better you get at it. Like, it'll become second nature, I promise. So, again, just because there's a negative here doesn't affect the period. The negative just means you flip the graph upside down or backwards. That's all. Okay, why don't we skip this slide here just in the interest of time? You guys feel like you got the idea of how to figure out amplitude period? Okay. Translations then. Well, if you were to then add or subtract a number afterwards, all that happens is you literally pick the whole graph up and slide the whole graph up and over or side to side. But I don't really see much point in spending too much time talking about this. All that's going to happen here is your sine graph, rather than, here actually, this is what it should have looked like. Well, if I lift the whole thing up too, it's now going to look like this. See how I pulled that off? I just literally slid the whole thing up. That's all. Same thing here. The plus D or minus C, whatever letters we use, the really important thing is it in the brackets or not? If it's inside the brackets, it goes side to side. If it's not inside the brackets, it goes up and down. Okay, so I got some more pictures here, but I think I've made my point. Do you guys get these diploma questions in yours? Where does it stop? At the diploma question I gave you. There's one more? Okay. Why don't I hop to the diploma questions now, and then I'll come back and I'll fill in the gaps, because I've covered more or less what I need to for the day. Let's see whether we can handle some of these questions now that I've taught you what we have. So try this one first. This partial graph of a trigonometric function is shown below. The graph has a maximum value at a, which is at pi over 2, comma 112, and a minimum value at 3 pi over 2, comma 28. We want to figure out which equation fits this graph. So let me talk you through a couple of options. Option 1, you could literally type in all 4 of these equations in your calculator. You could set your window to go from 0 to 120, from 0 to 5 pi over 2, and you could see which one looks the same, which is a lot of work, but it would work. Let's try some smarter ideas here. Do you see how this value up here is at 112? And this low value right here is at 28? In terms of raw distance, how far is it from 112 to 28? Like if you subtract the two numbers, how far is 112 minus 28? Okay, now 84 isn't your amplitude. 84 is how far it is from top to bottom. Hopefully you'd agree with me though, if you cut it in half, that would give you 42. That is your amplitude. Does that make sense? This graph is going to go up 42, and then down 42, and then up 42, and down 42. And I was able to figure that out by just looking at the 112 and the 28 values there. Downside. All of those had a 42, so that actually didn't help. But I did that one first because it was pretty straightforward. Well, why don't we talk about the last little bit here? See that plus 70 right there? You know what that plus 70 does is it brings the whole graph up 70. Well, let's say that you took 28 and you went up 42. Wouldn't 28 going up by 42 get you to 70? And then wouldn't going up another 42 get you to 112? Can you guys see how like 70 is like right through the middle of the graph? What goes right through the middle of this graph? Where is it directly slicing the middle of? Yeah, which makes sense because this is really the graph of sine of theta plus 0. This is the graph of cosine of theta plus 0. So normally the graph would slice right through the axes, but instead we've lifted it up. So would you guys agree with me that it looks like we've lifted it up one of the 70s? This graph is now 70 higher. So we've done two things. We've made it 42 times bigger, because it used to go from 1 to 1. It's now 42 times bigger. And we slid the whole thing up 70. So, I mean, at this point here, all I can do is just knock off A. I know it's not A. Well, the last little bit here. See how there's a minus pi over 2, or a minus 3 pi over 2. What does the stuff inside the brackets do to a graph? And with it being negative, it's going to move it that way, right? Now, where would a normal cosine graph start? Well, look, your normal cosine graph starts at its peak. But do you see how the peak right here has been slid over a little bit? How far over was it slid? There's our answer. said earlier today, this is infuriating to some people because, like, I literally did almost no work, right? Like, I mean, even the stuff I wrote on the board there, the 112 minus 28, you don't need to write that down, right? But if you can follow the logic behind it, I heard a couple of you had like a, oh, moment, right? Where you recognize, okay, I see how that works. So the minus pi over 2 slid this cosine graph. Normally cosine should have started here and gone up and down. That was really gross. But it got slid over by pi over 2. Let's try another one. The point pi over 2 comma negative 2 lies on this graph. We want to find the value of a. I have been preparing you guys for this question since grade 11 because this is one of those stupid leading coefficient questions where I'm really asking you to find what this a value is right here. Yeah, sure. Same sort of concept here though, right? This pi over 2 and this minus 2 are really your x and y value. Could you not plug in negative 2 for y, pi over 2 for theta, which is really x, and then solve? The downside here is kids get freaked out because they see pi over 2 and pi over the 4 and they absolutely just go, oh my goodness, I can't handle this. But don't freak out too much. Just take it step by step. So is everybody okay with how I just plugged in a negative 2 for my y value and a pi over 2 for my x value? Okay. Hard problem here. What is half of pi minus a quarter of pi? This is the thing that throws most kids off. If you have a half and you minus a quarter, what's left? You're right. If you had half a dollar, 50 cents, and you minus a quarter, 25 cents, you would have a quarter left. This is the spot where most people then just have like a freak out moment. They're like, I don't know trig. But like, you do. Oh, sorry, that's not pi over 2, that's pi over 4. What is pi over 4 equal to in degrees? 45. 45. Okay, so let's say I give you a 45-degree triangle. It goes 1, 1, root 2. You guys remember that? So cosine is adjacent over hypotenuse. So what I could do is I could take this whole cosine pi over 4 bit, and I could say that it's equal to the adjacent over the hypotenuse, which is the adjacent over the hypotenuse. I can just replace that whole stupid mess there with 1 over root 2. For sure. So most kids then, once they get to the spot here, they freak out over, well, how do I deal with cosine of pi over 4? But isn't pi over 4 this 45-degree triangle right here? Which we hopefully remember is like the 1, 1, root 2 triangle. Well, if this is your angle right here, cosine is the adjacent over the hypotenuse. So rather than write cosine of pi over 4, which kind of freaks kids out, just replace this whole thing with 1 over root 2. Well, now it's actually not that bad to solve for a by itself. To isolate for a, add 4 to both sides, which means that 2 equals a times 1 over root 2. And then to get a by itself, just times the root 2 up, and it gives you 2 root 2 equals a. That's your answer. I think in individual steps, you guys can do all of those steps, but my impression is most kids freak out over these first 2 steps here. The pi over 2 minus the pi over 4 freaks kids out because they hate fractions, and fractions of pi make it even worse. But then the other step here of remembering that cosine of pi over 4, I can just make that into like a fraction like this. Well, from there, it's just algebra. Now, this one asks you to get it to the nearest tenth, so all you got to do is just type in 2 root 2. But in theory, they could make a numeric response and make it a root b equals a, and then your answer would have been like 2, 2. So, classical music. You guys able to follow that one? Okay. If this cosine of pi over 4 bit stresses you out too much, I guess in theory what you could do is just literally type in cosine of 45 to get yourself this decimal number, and then you could then do like 2 times, let's see here, this must be 1 divided by root 2, must be kind of the, that's not, well, I'm going to screw that up, because then radians, never mind. Let's do cosine of pi over 4. Okay, see how cosine of pi over 4 is 1 divided by root 2? So if you wanted to, you could have used this decimal number the whole way through here. The only downside is if it wanted an exact value like this, you wouldn't have gotten it right. But if it just wanted a decimal number, then you could have just, made this 0.707 and just did 2 times by 0.707 kind of thing. Let's try one last one. The transformation g of x, or g of theta, is equal to f of 2 theta minus 2 is applied to the graph of sine theta. What's the new range? So this is meant to be really wordy to mess with you. Let's take it piece by piece. What does sine of theta look like? What is currently the range of that graph? -1 to 1, yeah. Go low to high, but same concept, right? So normally this graph would look like this, and it would go from -1 to 1. You get the idea, right? What is this 2 theta going to do to the graph? Yeah. There's now, rather than one of these things being in this time frame, there's now 2 of them. It goes twice as fast. Right? It's increased its period for what we're doing in physics right now. That would decrease the wavelength, thereby giving it more energy if you want to talk about that sort of stuff. Right? So how does that affect the range, though? Doesn't in the slightest. What does the -2 do to the graph? Down 2. So it used to get as high as 1. Slide it down 2, it's now -1. 1, slide it down 2, it's now down to -3. Okay, now there's 2 possibilities here that could possibly fit. Which one's more correct? Yeah. Because isn't your range your y values and your range your x values? Only x we're writing in theta instead. So x and theta are the same thing. That makes sense though? Yeah, because like x and theta are essentially the same thing, right? See how they did g of theta right here? But it could have been g of x. Same thing. Your calculator, even when you press the x button, so it does like x, t, n, and theta, kind of just means they're all interchangeable. So, okay, let me do a quick summary and then it's time to go here. So what we talked about today is basically the idea of how that unit circle correlates to these 2 graphs, which are basically identical waves. One is slid behind each other. I like this thing because it helps me visualize how there can be 2 answers. There can be an answer in 2 different quadrants. Does that make sense? And then the other thing we can do then is talk about how to manipulate this graph and make it taller or wider or slide it all over the place, right? And that can be useful in solving an equation. Can be useful. There's more than one way of solving things. So tomorrow then we're going to talk about how to deal with tan, cotan, secant, and cosecant. And then we'll take a day off to do some work. And then I'm going to do a lesson where we're going to kind of do a summary of both of these things we've been working on and try to put it all together. Okay? And then after that we'll try a quiz. So, sound good? Okay. Thanks, guys. We'll you guys can take off. I guess we'll talk to you tomorrow. First day back, eh?